Hello, and welcome to the first in our series of videos on the amazing normal distribution. You might be asking me, hey Mayberry, didn't we already talk the shit out of the normal distribution? Didn't we do things like derive the maximum likelihood estimates of mu and sigma? Didn't we already compute some hypothesis tests and look at the likelihood ratio test statistic? Well, yes, you're correct, but we've really just started to scratch the surface of inference with this crazy curve. So on the first page here, I just wanted to present to you two examples, which you probably have seen in the past, of real-world situations that can be modeled with a normal curve. On the left, you have SAT scores from a single snapshot year in time here, and on the right, you have birth weights of all babies. I think it was born in North Carolina in a specific year. See that both of these are situations where we see this bell curve structure start to arise. So, as a motivation for what we're going to do in the next few videos, I wanted to go back to the Guinness beer sampling example we discussed in class. You'll recall in that example that we were looking at a situation where Guinness beers have an alcohol by volume content which is normally distributed with a mean of 4.1 and a standard deviation of 0.1. So in our typical notation for the normal distribution, this would be mu and sigma. Now, a quality control problem related to this would be to sample a fixed number of beers from a new batch. For example, we had looked at the situation where you sample 5 beers and record the ABV measurements of those 5. And then the next question you would want to ask is, do these 5 measurements sort of provide some evidence that the mean for this new batch, right, the population mean for this new batch differs from what you'd expect if this was a typical batch of beer? So the hypothesis test we set up in this situation was we defined mu to be the mean ABV for the new batch of beers that was coming off, right? And our hypothesis test was mu equal to 4.1, the value you'd expect under the status quo assumption, versus mu not equal to 4.1. So the way we performed this test was we start off with defining z as our kind of primary test statistic. So z was the sample mean of the 5 observations minus the mean you'd expect under the null hypothesis over sigma square root of n, right? Now, in this situation, we plugged in the known values for sigma and n. And then our rejection region, right, was to reject h naught if the absolute value of z is greater than that typical 95% cutoff for the normal curve. Of course, all this is assuming that we're working with our normal significance level, right, of 0.5. Okay. Now, that's all well and good, and the thing that makes this work is, well, given that we know sigma, right, so in this problem this is a known quantity, we know the exact distribution of z, it's a standard normal. Okay. But the question we want to ask and develop in these next few notes is, what happens if sigma is an unknown quantity, right? So now we don't know. Well, the natural thing to do is replace sigma with what we have called in the past the sample standard deviation. Okay. The sample standard deviation, you'll probably recall, is defined as the square root of 1 over n minus 1 of the squared deviations from the sample mean for our sample. Right? Let me extend that square root sign a little more. But when we replace sigma with s, the result, the test statistic here, is now, you'll notice, a ratio of 2 random variables. Right? So this might not be a big deal. So let's check. So what I did, just to kind of motivate what's going to come next, is I ran a few simulations. Let me go back for a second. I'm going to call this ratio here t as opposed to this one, which will be z. Right? So I ran a few simulations. What I did is I ran about 10,000 different simulations. Each simulation we randomly sampled n equals 5 beers. Right? So we pretended we're getting 10,000 new batches and doing this procedure. Okay. Now, on this side are the z statistics. So this is the y bar minus 4.1 over 0.1 square root of 5, right? Okay. And the red lines here are the critical values, right? So these are the critical values, which, were 1.96 and negative 1.96 respectively. And as you can see here, right, we choose these so that the area outside is about 0.05, right? That's our type 1 error for this test. Now on this side, instead of computing this for each of our samples, I computed the quantities s over square root of 5. So now remember, s is a random variable. It changes from sample to sample. And what you notice here, right, is that there's this problem, because if we look at how many samples are outside the critical area, so these red lines are the same on both sides, right, this is much greater than 0.05 of the total, which means what we're going to have here is a lot of batches which are falsely rejected. So we're going to increase our probability of a type 1 error. Guinness is going to be wasting a lot of beer, and that's no good for anyone. So our goal for these next few notes is going to be discuss what is the PDF of this statistic, right? And as I mentioned earlier, the way we're going to handle this is by treating it as a ratio of two random variables. And so these notes are kind of going to lead us through the idea of how to compute the PDFs of transformed random variables, right? And we're going to do this for 1D transformations and 2D. Okay. The questions that we're going to address along the way, I think, are some pretty fun ones. So first of all, in the next video, we're going to talk about what is the chi-squared distribution and how is it related to the normal. Then we're going to answer the age-old question, why the hell is gamma of 1/2 equal to square root of pi? What do those two things have to do with each other? Finally, I know this is a big kicker because they never really talk about this in Intro to Stats, but why do we actually divide by n-1 in the sample standard deviation? Fourth, we're going to talk about a topic that's really more of a Calc 3 or multivariable calculus issue, but we're going to discuss a little bit how do you perform bivariate transformations of random variables. And then finally, what is the t-distribution and why do we have so many distributions named after letters? So just to give you an idea of what's going to take part in the rest of this video series, in the next video, we're going to talk about what is the chi-squared distribution. Okay. And chi-squared is usually denoted by the Greek letter chi with a square on top, a big surprise there. Okay. In part 2, we're going to discuss the Jacobian and 2D transforms. In part 3, we're going to actually come back and discuss what is the t-distribution and how do you actually derive its PDF. And then finally, in part 4, we're going to return to our original problem of how do we actually do inference with the amazing t-distribution. So I hope you'll hang out through the rest of these notes and check out what we got to offer.